Hello, this lecture is about the power series. Last lecture we talked about sequences, and these ones are all going to be about series. So the first one we're talking about is what do you mean by a series? So say for example, I wanted to add these numbers right here. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 132 plus 164 plus on and on and on. If I did that, if I eventually added all these numbers and continued this pattern, it would equal 1. If you want a visual representation, take a look at this picture right here. If I added a half plus a fourth plus an eighth plus a 16th and kept going half and half and half and half, eventually I would get a perfect square. This is what you call an infinite series because it goes on forever. And we also talk about it, this is called convergence, where if I add everything up, it approaches some value. However, there are some series that do not converge, and that's called diverge. So for example, what if I added this series together, or this sequence, 1/1, 1/2, 1/3. If I added these all up, it wouldn't converge. It wouldn't give me a number if I added them all up. So that's called diverging, or it's not converging. Whereas this one is one that converges. So in an infinite series, you take a term, plus another term, all the way until you get to infinity, and you get a series. This is the what you call, I think we talked about this a little bit earlier, but this is called sigma notation, where I'm looking for the sum of all of these from 1 to infinity of some term, a sub 1, a sub 2, a sub 3, whatever. A1, A2 are called the terms of the series, so this is called a term of the series, and a to the n is the nth term. Okay. There's another definition you need to know, it's called partial sums, where we just sum up part of the series. So S1 means just the first term, S2 means add the first two terms, S3 means add up the first two terms, and so on and so forth. Or a formula for that could be the partial sum n is from 1 to n. Okay, so S5 would be add up all the first 5 terms. Okay, if the partial sum has a limit as n goes to infinity, then the series converges. If not, it diverges. Okay, so let's look at what they call a geometric series. We talked about this last time. If you remember geometric series, they multiply something to get the next term. So do you see how in this one they have a, and it's multiplied by r, and it's multiplied by r again, multiplied by r again, and keeps on going on forever. Okay, this geometric series particularly converges when a, which is the first term, over 1 minus r, the r being the thing that you're multiplying by. If r is less than 1, but if it's greater than 1, it diverges. Okay, so that tells me that from -1 to 1, I have what they call interval convergence, or an area or part of the series where it does actually converge or reach a certain part. So here's an example. So I have 3/10 plus 3/100 plus 3/1000 plus 3/10,000, etc. Or those of you that don't like fractions, here it is in decimal form. Okay, you notice that if I plug in the formula, if I look back, oops, sorry. Remember, this is my formula, a over 1 minus r. This tells me if it converges. Okay, so a is 3/10. So in the a over 1 minus r, do you see I put in 3/10? R is what am I multiplying by? Do you see each of these terms is the previous term multiplied by 1/10? So multiply 1/10, I get 100. Multiply 1/10, I get 1,000. Multiply 1/10, I get 10,000. So a is 3/10 because it's the first term, and 1/10 is r because it's what is being multiplied by all these terms. When I plug it into the formula, I get 3/10 over 9/10, which is 3 over 9, or 1/3. That tells me that this series converges because if I add all these up, I get 1/3. Here's another example. I have 1 minus a half plus a fourth minus 1/8. Okay. You may notice again a is my first term, so a is 1. Okay, and remember my formula is my formula is a over 1 minus r. A is 1, so that's where I get the 1 from. R, you may notice I'm multiplying each term by -half. That's how I get -half. That's how I get -half times -half is 1/4. -half times 1/4 is -1/8, and so on and so forth. I plug it into the formula, I put it in here, and I get 2/3. And again, I found out that this series does converge, and it converges at 2/3. The partial sum of a geometric series looks like this. The sum, Sn, is equal to a over 1 minus r, just like the regular series. Remember we talked about it. But instead, they put another parenthesis here, 1 minus r to the n. Okay? If r is less than 1, this thing turns to 0, and I just get a over 1 minus r, which is just what we've been talking about. So every time it's less than 1, I can just use this formula. But if it's something else, I'm going to use this formula. So if x is less than 1 and we feel that r equals x, then again I get 1 over 1 minus x. Okay? So here's what the power series is. Again, this whole section is about the power series. The power series, here's the formula. It's the sigma notation, or the sigma, or the summation from 0 to infinity of some coefficient times x to some power. Okay? So the power series is a specific series where you have some number, and then you notice these x's, it goes x, x squared, x to the third, and so on and so forth. That is the power series. The c's are coefficients, they're just numbers, so this could be like 1, 2, whatever. And then a, which we've been talking about already, a is what they consider, the term is called the center. Okay? So whatever you're multiplying by, or x plus or minus a, that's what you call the center of the series. The first series would be centered at the origin. So this one, you see it's just x by itself. So this one has a center of 0. This one says x minus a, so a is going to be my center. Basically, I'm shifting over just like graphing. So here's an example. So once we have a series that we know, we can find a new series by doing the same thing to the left and right-hand sides of the equation. So for example, this is 1 over 1 plus x. We know that this is a geometric series with an a of 1 and an r of negative x. Remember, it's 1 minus r. So if this is plus x, that means r is minus x. Or in other words, this is what the series looks like. 1 minus x plus x squared minus x to the third, or whatever. Okay. Now, to find a series for 1 plus x, what we can do is just multiply both sides by x. Or find a series for x over 1 plus x. So say, for example, you know this already. Okay. But I say, hey, can you tell me the series for x over 1 plus x? All I do is take what I already know and multiply each of these terms by x. So do you see how this and this are the exact same thing, except for instead of 1, I have x, instead of x, I have x squared. All of these terms are multiplied by x. Here's another example. Again, we already know 1 over 1 minus x is 1 plus x squared plus x to the third. Now what if I said, find the series for 1 over 1 minus x squared? Okay. Well, one thing you may notice is that the derivative of 1 over 1 minus x, if, again, this is an example, if you know the derivative of 1 minus x is 1 over 1 minus x squared, which is this line right here, okay? So if I say, hey, take the derivative of this, well, that's the same thing as 1 minus x to the negative 1, which is the same thing as this, which is the same thing as this with a negative 1 out in front, okay? So if I want to know the series for this, what they said is, if this is the derivative of this, then I can take the derivative of all of these terms to find the series. So if this is true, okay, and this is the derivative of the left side, then I will find the series by taking the derivative of everything. So 1 over 1 minus x squared is equal to the derivative of everything. The derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, the derivative of x to the third is 3x squared. So they differentiated every term to get the answer for that one. And lastly, the most difficult example is, here again is the power series 1 over 1 plus x, and we already know it's 1 minus x plus x squared minus x to the third. What if I said, hey, find the series for ln 1 plus x? Again, you may not know this upon looking at it, but ln 1 plus x is actually, or the antiderivative of 1 over 1 plus x is ln 1 plus x. Okay, so it's like, hey, what do you know? This, if I take the antiderivative of this, I do get ln 1 plus x. So just like last time, instead of taking the derivative of everything, what if I take the antiderivative of all these pieces? And it'll tell me what that is. So here we go. 0 to x of this is the same thing as antiderivative of all these pieces. The antiderivative of all these pieces is x. Again, minus half x squared plus 1/3 x to the third. So all of these, I just take the antiderivative of each of the sides. Okay. So the previous examples of infinite series approximated simple functions such as 1/3 or 1 over 1 minus x. This series will allow us to calculate a function to as much accuracy as we'd like using only a pencil and paper. So again, we are finding series that maybe we couldn't have done as easily, but we're doing this using only paper and pencil. So that is what they call the power series. I know it's complicated. All I'll have you do is write a little summary of what you understand the power series to be, and then I'll get to the next video. All right, take care.